Hi, welcome to Real Learning Center. So we have been discussing a couple of topics all the sessions. So as you can see here, we have covered first positive and negative numbers, then we covered partition of numbers, and in the previous session we covered what are factors and multiples, and we will take the discussion ahead today and discuss about the very interesting concept of prime numbers. Under prime numbers, we are going to see first, what do you mean by a prime number, what's its definition, and what are the various important facts, like how is prime number of a keen interest to all of us. Then we will see what are the nature of prime numbers, how do they behave, and also how to find out whether a given number is prime or not. So we are going to see it. So let's start. Now, what is a prime number? In our previous session, we have seen about finding factors. Let us take example of 6. Now, what are the factors of number 6? We also saw that for any given number, 1 and itself, they are always factors. But apart from them, so let us not consider them. Apart from them, how do you factorize 6? You can write 6 as 2 into 3. Now let us take another number, for example 8. You can write 8 as and factorize it as 2 into 4, or you can also write it as 2 into 2 into 2. So we have got factors other than 1 and itself in both these cases. Now let us take another number, for example 7. Now for 7, can we divide 7 by 2? No. 3? No. 4? No. 5? No. So in this way, the only factors of number 7 are 1 and itself, that is 7. These two are the only factors. So such numbers which has its factors, its only factors as 1 and itself, call them as prime numbers. So as I mentioned, factors in prime numbers, and especially definition of prime number is a natural number whose only factors are 1 and itself, no other factors. All such numbers we call them as prime numbers, and by definition 1 is not a prime number nor a composite number. Now what is a composite number? Any number which is not prime. For example 7 is a prime number here. Any number which is not prime, in other words a number which has factors other than 1 and itself. A number which has factors other than 1 and itself is known as composite number. In our example, 6 is a composite number, 8 is a composite number. So to begin with, 1 is neither prime nor composite, and 2, it's the first prime number because you don't get any other factors other than 1 and 2. Similarly for 3, you don't get any other. Now what about 4? 4 has factors other than 1 and 4, that is 2. 2 into 2 is 4. So 2 is a composite number. 4 is a composite number. 2 and 3 are prime numbers. What about 5? 5 is a prime number. 6, we have seen, it's a composite number. So in this way, given any number, you can say either it is prime number, or it's a composite number. Any number. So in our example, 7 is a prime number, 6 and 8 they are composite numbers. Okay. Now what is the history? When did people take interest in studying prime numbers? The concept of studying prime numbers dates back to ages, and a proper written record of it it started all about 300 BC by Greek mathematicians, and one of the prime mathematicians, important mathematicians who worked on prime numbers is Euclid. And Euclid, he worked a lot on prime numbers, and he proved a couple of very fundamental and important theorems on prime numbers. As we can see here, Euclid proved about infinitude of prime numbers. It means that when prime numbers, are they finite? It means that, okay, now we found out that 2 is a prime, 3 is a prime, we found out. Similarly 5 is a prime, then you go 7 is a prime, like this you go on. But after certain numbers, for example, you have 21, this is a composite number, 22 is a composite number, 23 is a prime number, 24, 6 into 4, 24, 25, 5 into 5, like this you go, 27, 9 into 3. So what you can understand here, in between 2 and 10 you have 2, 3, 5, 7, 4 prime numbers, but between 21 and 30 you have got only 2 prime numbers, that is 23 and 29. So you keep go on. Okay, is there any last prime number after which there are no prime numbers? Can we say that? So Euclid proved a theorem. We are going to see about that in our session today. And then he also proved another very important theorem. He showed what he called as fundamental theorem of arithmetic. So we are going to study about that. Very interesting. And we are going to study about fundamental theorem of arithmetic in our next session. And then sieve of Eratosthenes. Eratosthenes is again a Greek mathematician, and he developed a technique to discover prime numbers. By end of today's class, we are going to learn the technique which is called as sieve of Eratosthenes. And this concept of prime numbers, it was a sort of interesting only to mathematicians, or in general to say those who study number theory in mathematics. That was the case till 1970. But during 1970s, this concept of prime number gained a lot of importance. And why? Now I gave you number 6. So number 6, can you factorize number 6 into 2 factors? Of course, other than 1 and 6. Yes, we have done it. 2 into 3 is 6. Similarly, can you factorize a number, say 49? Yes, 49 is 7 into 7. Similarly, can you factorize a bigger number, say 153? Well, we need some time to think. Slowly. Yeah, okay, it's about 17 into 9. Okay, so like this, I go on building, and suppose I give you a number like this, big number, 1,75,239. Now, can you find its factors? Oh, it's quite difficult, because you have to start dividing it by 2, then 3, then 4, then 5, then 6, it goes on. Now I have got 6 digit number. Imagine a 10 digit or a 20 digit or even 50 digit number. I have got such a big number, and now to factorize it into 2 other numbers, especially 2 other prime numbers. So it's a very difficult task. Hence, what they designed is called as public key cryptography. Means, suppose I am going to send message to another person, and I don't want that to be read by any other party. And what do? I code it. In the sense, I put it in a file and I encode it, and the receiver will have the key to decode it. Only then he can read the message. So now I have one key to encode, and the receiver has another key to decode it. So in this way, This is called public key crypto system or cryptography, where they used the concept of factorizing a very large number into two, again, large prime numbers. So in this field of prime numbers gained a lot of interest, and people started making lots of money by studying prime numbers. That happened in 1970s. So in this way, what we are going to study today, it's a very, very interesting topic, and also very fun to do, and also very, very valuable to the field of mathematics and computer science. Now, some other interesting facts. Yeah, there are infinitely many primes. As I told you, start with first prime 2, next prime 3, next prime 5, next prime 7, and next 9 is not a prime, next is 11, the next is 13, goes on and on. Is there any last big prime number? After that there are no more prime numbers? Can you say that? No. I mean, there are infinitely many primes. How do you say that? So there is a small proof, interesting proof, which we are going to see in our class today. And the largest known prime number has about 23,249,425 decimal digits. Such a huge number. And people who discovered such kind of huge numbers, they earned in millions. So this is the largest known prime number. I mean, this is not the number, this is number of digits in that largest known prime number. And this field of prime numbers, there are a couple of very interesting and very simple problems, but nobody has proved them. So, couple of unsolved problems in the field of prime numbers. First, are there infinitely many? We know, means there is proof for infinitely many prime numbers, but are there any infinitely many twin primes? Now, what is this twin prime? Twin prime is a set of prime numbers. You can see, for example, these two, or even these two, or even these two. Set of prime numbers, I mean, couple of prime numbers, two prime numbers, such that there is only one even number between them. I mean, the difference between them is 2. 5 minus 3 is 2, 13 minus 11 is 2, 19 minus 17 is 2, and there is only one even number between them. Such prime numbers are called as twin prime numbers. Now, as you go on, as I told you, next you get 23. After that, there is 29. You don't get twin prime here, but it again reappears. If you go to 30s, I mean future, if you go to 30s or 40s or 50s, like that, so it again reappears. Now, can we say, I mean, there are infinitely many twin primes? So initially it is more frequent, but as you go on, it is reducing. But you can never rule out that they don't exist. You may get twin prime in thousands or in 10,000s. You may get. There is a possibility, and nobody has proved or disproved it. That's an unsolved problem. Very interesting problem. And then a very, very important problem here, and this is known as Goldbach's conjecture. It's in about 18th century. Goldbach stated this, and till today it is not proved. And the statement here you can see here: every even integer greater than 2. I mean, 2 is the first even number, greater than 2. Say every even integer, say 4. It can be expressed as sum of two prime numbers. You can express 4 as 2. And next, 6. Can you express it as sum of two prime numbers? Of course, 3 plus 3. Next is 8. How can I express it as sum of two primes? 5 plus 3. Now next, okay, suppose we take a random number 22. Okay, you can express it as sum of two primes. So in this way, every even integer can be expressed as sum of two primes. So we are able to see it for our limited set of values, but can we say for every even integer? It's not yet proved. I mean, it's a challenge which mathematicians are still trying to solve it. Okay, next. And prime gaps. As I mentioned, between 10 to 20, we have got 4 prime numbers, but between 20 to 30, we have got only 2 prime numbers. But we cannot say that after 30 we can get only 2 prime numbers. I mean, between 30 to 40 only 2 primes, between 40 to 50 only 2 primes. We cannot say that. Suddenly you may get again 4 primes, or you may not get any prime number between say a given interval in the future. It's said that between, I mean, after 89 the next prime number is 97. So the prime gap, when the gap between 2 consecutive prime numbers, here it's 8. The first time the gap of 8 is introduced between 89 and 97. Till then you can see the gap is about 2 or say maximum 6. First time the gap of 8 is introduced. So in this way, this concept of prime gaps, or in other words, what is the gap between 2 consecutive prime numbers? We cannot say it is like this. It keeps varying. So it's a big, interesting topic which mathematicians are trying to understand. Okay. Now we'll come to our one statement what we made at the beginning of today's discussion about there are infinitely many prime numbers. How can you say there are infinitely many prime numbers? So let us try to understand this problem and let us try to prove it. Now to start with, the first prime number. Again, as I told you, 1 is neither prime nor composite. So the first prime number is 2. Okay. And what is second prime number? 3. So I will write one below the other. So we call first prime P1 as 2, second prime 3 as P2, third prime 5 as P3. Okay. Now I multiply P1 into P2. What do I get? 2 into 3. Suppose I add 1 to it. Now I got a number 7, which is a prime number. Yeah, 2, 3, 5, P4. Okay, I mean the fourth prime is 7. So we got a prime number here. Now suppose I do like this, P1 into P2 into P3. What do we get? Again plus 1. Same as 2 into 3 into 5. Plus 1. 5 3s are 15, 15 2s are 30. 30 plus 1, 31. Again, 31 is a prime number. So it's a very interesting fact. But can we definitely say product of, starting from first prime P1 up to say P2, P3, P4 up to a certain number, say Pn, P1 into P2, can we say P1 into P2 into P3 up to Pn to nth prime plus 1, can we say it is a prime number? Say a new prime number, capital N I am using, a new prime number. It's a new prime number. Can we say this? You have seen the example here. In these 3 cases it's valid. But can we generalize it like this? Okay. So let us keep it aside for a minute. And one important concept which I just mentioned at the beginning, Euclid's fundamental theorem of arithmetic. So what does it say? It says that you take any number, say for example I take 6, you can take any composite number, of course, you can always write it as product of prime numbers, always. Now for example you take 12, now how do you write 12? 4 into 3. Now 4 is a composite number, but if you further break 4 as 2 into 2, so you get all 3 as prime numbers. So in this way 12 could also be written as product of prime numbers. Similarly, the fundamental theorem of arithmetic, what Euclid has stated, it says that any composite number can be expressed as product of prime numbers. Product of prime, these are all prime numbers. Okay. Now let us keep this understanding in our mind, and we are going to study about this in our next session in detail. Let us come back to our question. Now let us assume that there are only finite number of prime numbers. So we said P1, P2, P3, P4, and let us go like that. Assume that the last known prime number is P of n. It may have 10 digits or 20 digits. In fact, we saw 23 million digits. So let the last known prime number be Pn. Okay, fine. Now if I am able to show there is one more prime number bigger than Pn, then I cannot say Pn as the biggest prime number. So the new number what I showed will be the bigger prime number than Pn. Okay. Then if I consider my new number, that is say Pn, if I consider this as my biggest prime number, I can repeat the same logic. P1 into P2 into P3 into P4 into Pn again into Pn, and you can add plus 1 to it. So you get a bigger number which may be prime or not prime. Okay. So in this way the concept what I am trying to use is, I will assume Pn to be the largest prime number, and if I am able to show there is one more prime number, at least one more prime number which is bigger than my largest known prime number, then my assumption is wrong. It means number of prime numbers are not finite, they are infinite. So now the task is, can we get one more prime number which is bigger than Pn? That is the task. How can we do it? So we have taken this number Pn as P1 into P2 into P3, product of all the prime numbers I know, including the biggest prime number. Okay, and I added 1 to it. Clear? So P1 is 2. It's an even number. So when you multiply 2 to any other number, end result is even number? True. Then I add 1 to it, it's an odd number. True. So Pn is an odd number. Now since Pn is an odd number, we have to check whether it's prime or not. It is. If it was an even number, then surely it was not prime. But since it's an odd number, we have to check whether it's prime or not. Okay. Now if I assume Pn is a composite number, okay, I am assuming it. Pn, where shall I write? I'll write here. Pn is a composite number. Oh, if it is a composite number, then what did I show here? Every composite number can be factorized into prime numbers. Into a product of prime numbers. Now I have taken Pn. What about the product of Pn? I'll assume it to be Pk into Pm. I assume it. So Pn is equal to Pk into Pm. Suppose it is a composite number, then I have two prime numbers, I mean multiply pk into pm, I get pn. Okay, fine. Now to see, I have got p1 into p2 into p3 up to pn plus 1. It means what? Pn is not divisible by p1. Pn is not divisible by p2. Pn is not divisible by p3. It is not divisible by pn. Oh, then pk is none of p1 or p2 or p3 up to pn. Pm is none of p1 or p2 or p3 up to pn. It means that pk and pm are two prime numbers bigger than pn. Then what does it show? It shows that there are more prime numbers than the largest prime number. Okay, then my theorem is proved. Or the second case, I assumed Pn to be a composite number. I will assume Pn to be a prime number. If it is a prime number, then surely it is bigger than P1 or P2 or P3 or P4 up to Pn. It's a very big number. Hence, it is bigger than the largest prime number what I assumed. Hence, I have got another new prime number. Therefore, prime numbers are always infinite. It may be a bit difficult to make sense of it completely. Try to hear it or go through this concept multiple times to strengthen it. So having known that the number of prime numbers are infinite, now let us see a very interesting topic known as primality test. What is this primality test? So given any number, say for example I have taken number n, say 27 for example. So to check whether this given number is prime or not, to check, the test is known as primality test. Okay. If it is prime, then it is prime. If it is not prime, then it is composite. Now, how do you check it? It's very interesting. One thing is I have to find factors. In our last session, we saw how to find factors. I mean, I start dividing this number by different numbers. So, I have 27. I start dividing it by 2. Does it go by 2? No. Does it go by 3? Yes. Sorry, 3 nines are. Yes, 3 nines are 27. Hence, it is not prime. Okay. Now suppose I assume the number to be 29. Okay, then by 3 it doesn't go. By 4, no. By 5, no. By 6, no. By 7, no. By 8, no. By 9, no. By 10, no. In this way, I will find out that it is indeed a prime number. Okay. Now, do I need to divide 29 by all the numbers before 29? Starting from 2, 3, 4, 5, 6, 7. Very time consuming. How can I quicken the process? So mathematicians found out that in order to check whether the given number is prime or not, then I have to check for only those numbers which are less than square root of this number. Now what is the square root of this number? 29. I mean, by taking the square of which number? Square of which number gives me 29? A bit difficult to find, right? Now let us go a smaller number, that is 25. Square of which number is 25? Or square root of 25 is what? So square root is denoted by the symbol. Okay. Square root of 25 is 5. Okay. Now I have 5. I mean, it means that 5 square is equal to 25. The same thing. Now I have this 5. Okay. Now take 1. 1 is always a factor of every number. So take 2. 2 into some number should give me 29, but it's not there because it's not divisible. Next 3. Okay. Next 4 and 5. Okay. 4, 29 doesn't go. 5, it doesn't go. But what about 6? Now what is 5 into 6? 5 into 6 is 30. I mean, I have checked for all numbers up to 5. Okay. And any bigger number if I take, that is 6 is a bigger number than 5. If I take 6, then the other factor must be less than 6. It must be 2, 3 or 4 or 5. True? So hence, it's enough for me if I check for those numbers which are less than the square root of the number. So in this case, so 29 is not a perfect square. So roughly I have taken as 5. So if I check whether 29 goes by these 4 numbers, that's enough. 29 goes by 2? No. It goes by 3? No. It goes by 4? No. Is it divisible by 5? No. That's enough. I don't have to check further because I know that because all the numbers lesser than or equal to 5 is already checked. So 6 square is 36, which is bigger. Is bigger than 29. Hence, I can stop checking at integer 5. So this is very important concept to understand that in order to check for primality, I need to check only up to the square root of that number. Okay. So now, in order to find out the divisibility, and now I told you for 29, you have to check for divisibility with 2, 3, 4, 5 and that's enough. I have told you. One way of checking divisibility is 29, you start dividing by 2, you get 2 ones are 2, then 9, 2 fours are 8, 1 remainder. Since remainder is not 0, this is not perfectly divisible. So in this way you have to perform actual division and then you find remainder is not 0. Therefore it is not perfectly divisible. Okay. Like this, if you want to check divisibility for 2, 3, 4 and 5 this way, so the process looks a bit tedious, takes time. Then is there any easier way to check for divisibility? That is known as divisibility test. Now for 2, we all know that 2 is even number. So every even number is divisible by 2. Okay. So divisibility test for 2. Take that number. If it is even, then it is divisible by 2. If it is odd number, it is not divisible by 2. And what is the divisibility test for 3? The technique is like this. Take that number, given number, say in our case it is 29. Add the digits in that number, that is 9 and 2. Add the digits, 9 plus 2, you get 11. Is 11 a multiple of 3? It means that when you factorize 11, do you get 3? No. Hence, it is not. So to check for a divisibility of 3, add the digits and check whether it's a multiple of 3. If it's a multiple of 3, then it is divisible, else it is not divisible. Of course, you can further continue here. 1 plus 1 you can add it as 2. Again, 2 is not a multiple of 3. Hence, it is not divisible. In this way, we can find the divisibility test for 3. What about divisibility test for 4? We know that 100 is perfectly divisible by 4. So in this way, 100 or 200 or 400 or 500 or 600, all these hundreds are always divisible by 4. So it's enough if you check for only the last 2 digits, because any other digit this side, for example if it is 129, 100 is always divisible by 4, and so you have to check only for 29. Okay, 29 is not divisible by 4, you know the tables, 4 sevens are 28, so it is not divisible. So in this way you can say. And what about divisibility test for 5? If a number is divisible by 5, it has to end with 5 or 0, only then it is divisible. Now what about divisibility test for 6? If a given number is divisible by both 2 and 3, only then it is divisible by 6. Yeah, both 2 and 3. Given in a number, if it is divisible by both 2 and 3, then it is divisible by 6. And what about 8? For 8, you have to check last 3 digits, means say we have got 2153. Only check for these 3 digits. Perform actual division only for last 3 digits. If it is divisible by 8, then the entire number is also divisible by 8. Otherwise no. And what about 9? 9 is very similar to 3. What did you do for 3? You added the digits and then found out whether it was a multiple of 3. For 9, add the digits and check whether it's multiple of 9. So 9 plus 2 is 11 is not a multiple of 9. So it is not. And what about 10? Very easy. If the number is ending with 0, then it is divisible by 10. Otherwise, so in this way, simple divisibility test to check whether the number is divisible by starting from 2, 3 to 10 we have seen. So this can be used to check whether a given number is prime or not. How to check? If the number is divisible by any of these numbers, say 2 or 3 or 4 up to say 10 or 11, then we can say that it is not a prime number because it is divisible by other numbers. But if you are fully sure that starting from 2 up to square root of that number, none of the other numbers divide the given number, then the number is prime. Okay. Now we have taken a couple of examples here. So example 1, we are checking for divisibility of 440 again by 9. So what do we do? Add the digits. What do we get? 9. Okay. The sum is 9, which is a multiple of 9. Yes. So 441 is divisible by 9. So it is not a prime number. Next, primality test. So we have seen check for prime by performing actual divisions up to square root of that number. Now we have got number 343. Okay. Now what is the square root of 343? We may not know exact value of it, but we can guess it. For example, what is square root of 400? What is square root of 4? 2. So square root of 400 is 20. So square root of 400 is 20. 343 is a smaller number. So if I am able to check the divisibility up to 20, even 20 is not required. Less than 20, say 19, then that's enough. Okay. So let me check whether it's an even number. No. So 2 is ruled out. Now for 3, add the digits. 3 plus 4 plus 3, we get 10, which is not a multiple of 3. Hence, yeah, it is not divisible by 3. What about 4? Take these 2 digits. 43. 40 is divisible by 4. 43 is not divisible. Hence, it is not divisible by 4. What about 5? Large digit, that is 3 here, not 5 or 0. Hence, it is not divisible by 5. What about 6? Since it is neither divisible by 2, not divisible by 3, it is not divisible by 6. And what about 7? So 7 you have to perform actual division. Let us do actual division. 343. Okay. 7 4s are 28. 6 remainder 63. 7 9s are 63. Remainder is 0. So it's perfectly divisible by 7. Hence 343 is not prime. Quite soon we discovered, using the divisibility test technique. First we figured out up to what number I have to find out, to check for the divisibility. It came out to be say 19. Okay. Then I started from 2, 3, 4, 5, 6. Very quickly I could say that it is not divisible by none of the numbers, but 7 I performed the actual division and I found out it is perfectly divisible by 7. Hence the given number is not prime. I hope you got the grasp of the topic. So now, final topic for this session is sieve of Eratosthenes. In the starting of session, I mentioned 2 words about Eratosthenes. He was a Greek mathematician, and he found out a technique of finding out all prime numbers, up to a given number. Say for example, in our case it is 120. Up to this 120 is what I have taken. It can be 100 or 200 or 300 or 400 or any number for that matter. How do you find all prime numbers lesser than this given number? So he has developed a wonderful process or algorithm to find the prime numbers. So here we have listed all the numbers starting from 1 till 120. Now we also know that to check for primality, I have to start from say first prime number up to square root of the last number. Now last number 120. Perfect, it's not a perfect square. 121 is a perfect square. So up to 11. Square root of 121 is 11. So if I am able to check for divisibility starting from 2 up to 11 for all these numbers, that's enough. Okay. Now let's start. Number 1 is neither prime nor composite, so let us rule it out. It's cancelled. Now starting from number 2. Number 2 is a prime number, we all know that. Now what is the next multiple of 2? That is 4. And further 6, 8, 10, 12, 14 are all multiples of 2, hence they are composite. So let us rule out all those composite numbers. So this sieve, you all know about sieve. Sieve means what filters. In our home we use it usually for filtering atta or flour. I mean the solid particles we want to separate from the flour. So we use that sieve. Similarly, here we are filtering out prime numbers and removing composite numbers from the given list of numbers. So here we ruled out all the multiples of 2. Now next, what is the next number here in this column? 2 is over. The next number which is not yet ruled out. Okay, if I have ruled out 4, it means I have ruled out all multiples of 4 already. But here 3 is not yet ruled out. So I will take 3. 3 is a prime number. Now what is next multiple of 3? That is 6. But 6 is already ruled out because 6 was a multiple of 2. So it's enough if I start checking from square of 3, because any number less than square of 3 is already ruled out, because that would be a multiple of a number less than 3. In other words, 6 is a multiple of a number less than 3. So it's already ruled out in the previous step. Hence I will start only with 3 square, that is 9. Okay, 9 onwards all the multiples of 3, 9, 12, 15, 18. Okay, in this way all of them are ruled out because they are all multiples of 3. Hence they won't be prime. Now what is the next number here? 5. Now starting from the 5 square is 25. Starting from 25, all multiples of 5, 25, 30, 35, 40 are all ruled out. Now my third prime number is 5. Okay. Next, my next prime number is 7. What is square of 7? 49. So from 49 onwards, further multiples. 49, next 56 already ruled out, 63 already ruled out, 70 ruled out, next is 77. 49, 77 and 91. These 3 are over. Now what is my next number which is not yet ruled out? That is 11. And what is 11 square? 121. 121 is beyond my list. 120 is my last number. Hence, whatever number is remaining here, starting from 2 up to my last number, I have taken this example only 100 numbers, not 120, sorry, only 100 numbers. So what is my last number here? My last number is 97. So all these numbers starting from 2, 3, 5, 7 up to 97, my last number is 97. They are all, whichever is not crossed out, they are all prime numbers. Totally I have got 25 numbers. I mean the list of prime numbers between 2, I mean including 2 up to 100 is total 25 numbers. So using this technique of sieve of error testing is, we are easily able to compute list of all prime numbers starting from 2 up to that given number. I hope this particular algorithm is, impressed you and you are able to make good sense of this algorithm. In this way, we have come to the final leg of the session, that is some problems for you to work with to get further familiarized with the topic of prime numbers. So check for familiarity of the given following numbers. So today we saw this wonderful concept of prime numbers. What are prime numbers? Numbers which don't have any other factor other than 1 itself. And what is the history behind prime numbers, and what are the interesting applications of prime numbers. And we also saw how to check for, whether a given number is prime or not. So that is called as primality test. So in this way, we have learnt a very fundamental topic of mathematics. And in our next session, we are going to continue this discussion and further go into the study of prime numbers, especially prime factorization. That's it for today. Thank you very much.